Good morning. First of all, I want to thank Lionel for the kind introduction and also all the other organizers of the conference to give me the possibility to be here to present a work that as a group at the Italian Institute of Technology, we are working since 2016 when I established my group, and which we strongly believe can be a fundamental step or a fundamental revolution in the context of laser scanning microscopy. I'm sure if I tell you that laser scanning microscopy is one of the most popular optical microscopy architecture in life science, you are not surprised. The reason of that is because probably in any of your lab, you have one of them. But more in particular, the reason is that not only you can combine this optical architecture with fluorescence, just to give you sensitivity and specificity in your analysis, but also to many other advanced microscopy techniques. So some of them for sure you saw during this workshop, but let me mention a few of them to highlight. So first of all, confocal microscopy, so that provide you optical sectioning, so you can navigate across your sample, across all the three-dimensional space. Then to photon excitation microscopy that provide you the possibility to go deeper in your sample. Then fluorescent lifetime microscopy. I'm sure that this workshop, you touch a lot this topic that give you the possibility to have a sort of new dimension about your sample to investigate, for example, the physiology of your sample, or any way to make functional imaging. Or fluorescent fluctuation spectroscopy that provide you, that allow you to observe biomolecular dynamics directly inside living cell. So at the end of the story, this combination gives you to your laser scanning microscope a unique combination of spatial and temporal ability, and also an access to a vast pool of information. However, we, as a group, we think that anyway, this kind of characteristic can be further improved. And in particular, can be improved because we believe that there is a fundamental limitation in how the image are recorded in a laser scanning microscope, or more in particular in a fluorescent laser scanning microscope. So, and in particular, we believe that there is a lot of information that are lost during this image formation. So to try to convince you about that, and also to explain you how we want to solve this problem, let me start from the beginning, and let me start to introduce, not introduce, but to show you how a fluorescent laser scanning microscope works. So, so first of all, what you have a laser beam. In this case, is depicted by blue, that you use an objective lens to focus such a beam into your sample, and in particular in a specific position of your sample. Then all the molecules that are within this specific position, that typically is diffraction limited, so is in the range of few hundred nanometers. All the molecules that are in this region, that also we call detection volume, probing volume, excitation volume, are emitting light simultaneously. This light is collected by the same objective lens, and by the use of different mirror and other lenses, in particular the tube lens, is projected into the image plane of the microscope. Okay, so basically, in principle, here I have an image because I have a region, and in the image plane I have an image of my region. But here what happens? So typically, in the image plane of my detector, there is a single element detector, so such a photomultiplier that integrates across the space. So it produces, since it's a photomultiplier, it has a very high temporal resolution in the order also of gigahertz, but at the end it produces an intensity, a single intensity signal. So a signal that changes in time, but not in space. Then typically I have a data acquisition. My microscope has a data acquisition system that also integrates in times. So what does it, and then, okay, since it's a laser scanning microscope, I need to scan this spot, this diffraction limited region, or anyway, the probing region, the excitation region across the sample, until I build up my digital images. So that's basically how the image is formed in a conventional laser scanning microscope, in your confocal microscope as example. But it's clear that we are losing a lot of information during this process. So basically, I told you, you shine the light in a region, and in this region, there are different molecules that are distributed spatially, but at the end, and you produce an image, but at the end of the story, you integrated this image across the space. So you are losing the spatial information. At the same time, what concerns the time, because as I told you, since you have fluorescence, here you have a dynamics about the fluorescence. The signal is not static, but it's changing in time. And again, your data acquisition system typically integrate across the time. In the case of imaging, you typically integrate across the pixel dwell time of your system, of your scanning. In the case of fluorescence fluctuation spectroscopy, integrate across the time of the beam width of your time traces. So anyway, so we are losing a lot of information. So because we are averaging out a lot of spatial and temporal information. And we know from physics, but not only from physics, the average can generate some problem. So we are living in the area of single molecule, and you know what happened when people was able to move from ensemble technique to single molecule. So stopping making averaging, a lot of information came out. The same things can happen here if I will stop to make a spatial and temporal integration of the signal that came from the probing region of my system. So I can solve this problem. So clearly, for example, I can substitute my photomultiplier with a single photon avalanche diode, or anyway, a single photon detector, an APD, a SPAD, an hybrid detector. But in this case, still I will collect the light photon by photon. I can observe all the fluctuation at the single photon level of the signal, but I will still discard all the spatial information that potentially are encoded in the image of my probing region. Otherwise, what I can do, I can use a conventional camera like a CMOS, a CMOS, or a CCD. In this case, I will be able to make an image of my probing region. But since the CMOS, the CCD, and current technology has a limited time resolution, I cannot really observe I cannot really collect all the temporal information that can be delivered by my system, by the sample. So in 2016, it was clear from our side that there was a sort of lack of technology. So does not exist a sort of camera able also to preserve all the temporal information that potentially your sample can provide you. So what we do, we start collaborating with the Polytechnic of Milan to develop what, in our opinion, was the first detector specifically designed for laser scanning, fluorescent laser scanning microscopy, able to solve the limitation that I was able to explain you. So I don't want to go into the detail of this detector that we develop, because that's not the workshop for that. But I want to give you just a few important information about that. So first of all, this is a single photon. Okay, first of all, this is a very small detector. So as you can see here from this image, is only 5 by 5 element. So it's not like a megapixel camera like the one that used in wide field microscopy, but it's a very small detector. So only 5 by 5 pixels. But since it's only composed by 25 elements, I can transfer the data really fast. In particular, in this case, we implemented what is called an asynchronous readout of this detector. So every time that the photon arrives in one of these detectors, one of the elements of this detector, for example, the central element, like in this case that I'm pointing, so a digital signal will be delivered to the data acquisition system. So basically, this is a system that has no frame rate. So there is no limitation like in a normal camera in which you have a frame rate for the temporal resolution. Every time that a photon is collected by one of the elements is transferred to the data acquisition. The second important feature that every element is a single photon avalanche diode detector. So basically, every time that a photon is collected by one element, I'm sending out a digital signal to my data acquisition card, and this digital signal has a precision of few hundred picoseconds. So in this case, it's 150 picoseconds for this specific detector. So that means that I have fully access to the photophysical of the fluorophore. So small camera, 5 by 5 element, no frame rate, single photon ability, single photon detection, and single photon timing ability. So when we received this new toy, we were so happy into the lab. We immediately placed in our custom-made confocal microscope, and we immediately realized that effectively what we envisaged, that we can get access to many new spatial temporal information is true. And thereby we open a lot of different projects that try to improve any of the characteristics of the microscope. So from the spatial resolution to the temporal resolution the temporal range to the spatial range, and also try to improve the information content. So the kind of information, try to extract as much as possible information from the sample under investigation. We are also happy to know that, I mean, not to know, but we are also happy to see that many other people are working in this direction. I mean, Graton, for some perspective, is using similar system. Other group from the Weizmann Institute are doing the same stuff. So basically, we are confident that effectively having such kind of detector, such kind of pixelated single photon detector in a confocal microscope can be advantage for many different, to get as much as possible information from the sample investigated. So for question of time, obviously I cannot go through to the whole project that we are running currently based on this system, but I want just to touch a few of them. So the first one is a project in which we try to explore the new spatial information provided by the detector to improve the resolution of a confocal system, or in general of a laser scanning microscope system. And we do through the concept of image scanning microscope. So to start describing this project, let me do one step back and let me introduce the confocal microscope. So, or let me say a few words about the confocal microscope. So I'm sure that most of you know the confocal microscope mainly for its ability to perform three-dimensional imaging. So to have optical sectioning and allow you to navigate inside your samples across the axial dimension. So this ability is given by the fact that I play in front of the detector, and in the image plane of the microscope is located a pinhole, really a hole that is able to reject all the out of focus light coming from your sample. So, but I don't know if you are also aware by the fact that the confocal microscope was also the first effective microscope system able to overcome the diffraction barrier. Indeed, if you close the pinhole of your microscope, your confocal microscope, you do not only reject the out of focus light, but also you squeeze the Poincare function of your system. So I'm happy that Luca Lanzano already introduced the concept of Poincare function. So I think that you can understand what I'm going to tell you in the next. So as you can see here from this graph, when you close the pinhole of your confocal system, your resolution, the full real maximum of your Poincare function, decreased down to an improvement of a square root of 2. This improvement can be also seen from imaging from this calibration sample, some simple fluorescent beads. You can see that when you close the pinhole, if you move from the top to the bottom, you can better resolve this, you can better separate the nanoparticle in your sample. But why the confocal microscopy has not been considered as a true super resolution system is due to the fact that, unfortunately, when you close the pinhole, you are also losing in signal to noise ratio. So as you can see from this graph, here is the intensity as a function of the pinhole. Obviously, when the pinhole becomes infinitely small, you don't have any more signal. You do not collect any more light. So again, if you check the same sample, but using a slightly low dose of illumination, and this is typical in the case when you want to go to lifestyle imaging, in which you cannot crank up the intensity of the laser as much as you want. So in this case, here where I have a much lower flux of photon, if you move from the top to the bottom, again, because I'm closing the pinhole of the system, you will realize that at very low, so when you close the pinhole, you end up in an image that is just noise, and thereby the effective resolution is not, the improvement in resolution is not anymore evident. So that means that when you sit in front of a confocal microscope, you have always you need always to choose between resolution and signal to noise ratio. So what I'm going to show you is that by using the SPAD array detector, the single photon Avro-dyed array detector that I described you before, you can solve this limitation. And in particular, I want to show you how we can implement the concept of image scanning microscopy. I placed this slide because I'm happy to name in this slide a few people in which I work with. So Enrico Bertero was my PhD, one of my PhD supervisor. And the funny thing is that he introduced this technique in the 80s when I was a kid. The same things also, the same concept was also developed by Colin Shepard in the 88. And the nice thing is that only 20 years later, Enderlein was able to demonstrate this principle, the principle of image scanning microscopy, that I'm going to tell you much more in detail later. But the basic reason why nobody was able to implement it was the fact that there was a lack of technology. So it doesn't exist a camera that is fast enough to follow the scanning of your system, that typically is in the range of microseconds. Also for the implementation of Enderlein, let's say if he showed the possibility to improve the resolution by using a camera, but this was not really an effective implementation, again, because he used a conventional camera. A conventional camera are not fast enough to really support the speed of your scanning system. So anyway, so what we do, we take we remove the pinhole from our system, so you don't need anymore the pinhole, and you place and you substitute the typical single element detector, in our case was a photomultiplier, with our SPAD array. So as I told you, that's still a scanning system. Keep in mind this, you still need to scan your system, that's very important. But now for each position of the sample, for each scanning position, what we have an image. A small image, only 5 by 5 pixels, but for each position of the sample, we have an image. So that's a data set that we get at the end of the scanning. So 5 by 5 images for the number of pixels that you decide to scan. In such a case, for example, 512 by 512. So now that we have this data set, what we can simply do is to making a reshaping of this data set and to represent in terms of conventional images. So let's say basically we have, in this case, 25 images of 512 by 512 pixels. So basically each element of the SPAD array is able to generate one independent image of the sample. All these images are collected at the same time. So that's an example, that's a simulation. So this is a simulation of a single particle, so the imaging of a single particle. So basically it's the point spread function of the system. Every image is collected independently by one element of the detector. That's why we have 5 by 5 image of the particle. So it's interesting to see that basically they look pretty similar. So the point spread function, at least in the central part, is always a sort of Gaussian function. But what is very important in the context of confocal microscopy is that now we don't have any more a pinhole, and thereby we collect all the light emitted by the sample. So there is no anymore the problem of throwing away photon. But let's go a little bit more in detail. Let's try to understand which is the point spread function of each of these 25 images. Let's start from the central, the image collected by the central element. So in a confocal microscope, the point spread function is typically can be calculated by the multiplication of what is called the illumination point spread function, so the diffraction limited spot, multiply for the emission point spread function, the diffraction limited spot into the emission. So in these cases, if we assume that both the excitation and the emission are Gaussian distributed, and in particular, we can assume that also the Stokes shift is not relevant. So at the end, we have a multiplication of two Gaussian functions that will end up with a Gaussian function that is positioned exactly in the same place, but with a sigma that is reduced by a square root of 2. Let's see what happened to the image collected by the element on the right side of the central element. In this case, the illumination will stay the same, but what will happen is that the detection point spread function will be shifted on the right, simply because the element is slightly shifted aside the central element. So again, the point-spread function is the multiplication of the two point-spread function. Again, two Gaussian functions that multiply. If you multiply two Gaussian function, you get a third Gaussian function with a reduced Windle maximum. But in this case, what happens is that it's also shifted by half respect to the position of the excitation and the detection point-spread function. So practically, an identical point-spread function was shifted on the right side. For the left element, exactly the same things, but the PSF is shifted on the left side. So this is the point-spread function from the 25 element for the 25 image that it collects simultaneously with the spot array detector. As you can see, this is a video showing the 25 images. As you can see, this 25 point-spread function. As you can see, basically they are almost identical, at least at the center, but they are simply shifted one respect to each other. So when we have these 25 images, what we can do? So basically, for example, what we can do, we can sum them up, but this will be stupid because exactly what our single element detector was doing, integrating across the space. So, but in this case, so we end up with a point-spread function that is simply larger than the one of the central element. So the principle of Pixel-Reassignment, that it's the base of the image scanning microscopy, is not only to sum up the images, but before to shift them back. Since I told you at the beginning, basically at the end of the scanning, I have 25 images that represent exactly the same sample, but are simply shifted one respect to each other. What we can do, we can register such image and then make and summing them up. In this case, we are getting a narrow point-spread function, as you can see here, and we are also using all the photon collected by the detector. So we are not throwing away any photon. So this is a real measurement of a gold particle. So this is just a reflection mode, but this means that the same principle can be applied also to reflection and not only to fluorescence, as you can see here. So these are the 25 images of the particle. This one is the image collected by the central element. So basically it's like my confocal image in which I have a very small pinhole, in this case 0.2 area unit. As you can see, the resolution is pretty high, so to 230 nanometers, so in line with what we expected, but the number of photons collected is only 200 photons. If we sum up all the 25 images that we collect, we end up with a bigger point-spread function, so the resolution becomes worse. It's like we open the pinhole, but we collect much more photons. In this case, it's roughly 800 photons. If we apply Pixel-Reassignment, that is, I told you, is basically taking the 25 images and shift back register respect to the central images and sum them up. Then what we get, we have high resolution because we recover the resolution of a confocal microscope, also the square root of 2 enhancement. But at the same time, we are using all the photons. So here you see that we are more than 1,000 photons instead of only 200 photons. So high resolution and high signal-to-noise ratio. Another observation that I wanted to tell you is that, when you are sitting in front of a microscope, nothing is ideal. So you have always aberration, misalignment of your system. And thereby will be nice to establish a method that is also able to take into account about this aberration. For example, here, this is the metric of the shift vector, which represent the amount that I have to shift before making the sum, before summing the image. That's completely based on theory, so on the geometry of the detector. But then in practice, this is much different because you have aberration. So what we do, we develop an algorithm, so based on phase correlation, for which we register automatically the image and we sum them up later. So as you can see here, you further enhance the resolution and you further enhance the signal-to-noise ratio of your image. So some example of the method of the image of the Pixel-Reassignment image scanning microscopy approaches. That's an image of tubuline structure in which we make imaging of tubuline. This is an image collected, let's say, with a conventional microscope in which we have a closed pinhole. when we open the pinhole, you can see that the signal increase, but also the blurring increase, as you can also see by making intensity plot along this direction. Here, the blue is the confocal. So basically, the signal to noise is too poor to resolve some structure. If you open the pinhole, you get much more signal, but the image becomes blurred, and thereby you are not able to resolve the tiny structure in your sample. But if you apply image scanning microscopy, and in particular the adaptive Pixel-Reassignment method that I showed you before, you can clearly see that now I can resolve the two tiny structures that are present into the sample. You can resolve the two Tubuline structures that are close by. Since we are a lab also of computer scientists, we also combine this method with the convolution, in which you can clearly see that there is a further enhancement of the contrast of the images. So we'll go a little bit faster because I want to go to the second part of the talk. So that's a few other results using this technique, because I want to highlight the versatility of the technique. It's not like a STED that basically you need some specific fluoroform in some cases, or anyway you need some specific condition. Here is just a system that you can apply with any kind of sample that you have, that you typically use, that you typically observe with a confocal microscope. So, for example, here there are some is an imaging of some neuron spine in a tissue, in a slice of brain, up to 100, 200. We make imaging up to 300 micrometer in depth. Another example is here is the chromatin organization. As you can clearly see, there is much more detail in your adaptive Pixel-Reassignment images. So up to now, I just told you that you get an enhancement resolution, but I never quantify such enhancement resolution. Here I plot the resolution in terms of Fourier ring correlation analysis. That is a particular way based on the Fourier transform of the image to extract a value for the resolution of your images. These are the resolution as a function of the excitation power that you apply to your sample. As I told you, it's very important that when you are performing lifestyle imaging, you cannot really crank up the intensity of your laser as much as you like. So as you can see in all the three cases, confocal or open pinhole confocal and Pixel-Reassignment, there is a decrease of an improvement in resolution for increasing power. This is just because we improve the signal to noise ratio. But what is more interesting to observe is first that the reassignment, Pixel-Reassignment give you always the best resolution. And another very important thing is that if you check, you can get the same resolution with the Pixel-Reassignment, but with 10 times with image scanning microscopy, but with 10 times less intensity than in a confocal microscope. So that means that this technique is ideal for lifestyle imaging. So to demonstrate this, I just want to show you this experiment in which we make a time series. We make 20 frames, and the first 10 frame has been collected using a low dose of excitation, only 0.5 microwatt. The second 10 frame has been collected with 5 microwatt in order to make the confocal resolution similar to the resolution of image scanning microscope. So in particular, 2060 nanometer in resolution. So here is the video. These are the first 10 frame. As you can see, when we switch on, when we increase the intensity of the laser to 5 microwatt to achieve the same resolution with a confocal, then the signals start to fading because I introduce some photo bleaching and most probably also some phototoxicity to the sample. So this means that this is a technique that is designed for specifically for lifestyle imaging. So I still have some time to show another example, another example how we can improve the performance of laser scanning microscopy using the SPAD array. In these particular cases, we implemented the fluorescence lifetime imaging. So as I told you before, so we have a detector that is a single photon detector, and it has a temporal, can collect photon, can register photon with a temporal precision of 150 picosecond. But you know that when you need to implement the lifetime measurement, it's not only important having a good detector, but what you need, especially if you want to implement a time-correlated single photon counting experiment, you need also a pulse laser, and you need also a multi-channel time-to-digital converter. So a card that is able to register the photon with such high precision. In this case, our major challenge was the fact that doesn't exist a time-to-digital card able to collect up to 25 signals. So for that reason, what we do, this is a project that we did with Alessandro Rossetta. Basically, we develop a multi-channel and time tagging system. So, and I'm happy to tell you that this system now has been released under open source. So you can go to our website, our Git pages, and download both the software and always all the hardware component to having in your lab a time tagging multi-channel TDC card for implementing, for using the SPAD array, obviously, but also to use any other kind of single photon detector system. Just a few, okay, very important, this data acquisition has been developed using an FPGA. So that means that if you have the ability or any way, you can still working on that and try to improve the performance of this card or adding some new feature to the card. This is based also on an evaluation kit that you can buy for a price of 2000K, so relatively cheap if you compare to data acquisition system, similar data acquisition system that maybe cost more than 50K. So really fast, a few characteristics. This is a data acquisition system that can provide you a precision of 30 picoseconds. So well below the precision of the detector that was 150 picoseconds. It can be used with any, it has in principle an unlimited temporal range, so you can use with any repetition rate of your laser, and it has only 4 nanoseconds at time. So every time that the photon is collected, the card is blind for roughly 4 nanoseconds. But that's not a problem because already the detector is, every element of the detector is blind in the order of 10 nanoseconds. And the other most important thing is the fact that you can collect simultaneously signal from many different channels. So you can collect simultaneously signal from all your 25 channel for all the 25 elements of your SPAD array detector. So when we get this new card, we can combine with our SPAD array, with our scanning microscope, and we start immediately to make lifetime imaging. So as I told you before, since we have these 25, we collect simultaneously 25 images, and we can recombine them by Pixel-Reassignment and thus improving the resolution. Now we have a first lifetime system that is not only able to give you the lifetime information, but also to provide you high resolution map. So as you can see here from this example, in which we compare conventional confocal microscope with image scanning microscope, you end up with an image, an intensity image with high resolution, but also with a map with high resolution. So another example in the context of lifetime is here, in which we make imaging of a live cell. So again, one of the major characteristics of the system of this kind of technique that I'm proposing is the fact that you can do a live cell imaging in a pretty easy way, like you typically do with any other microscope, conventional microscope. So that's an example in which we use a polarity sensitive membrane probe, the ANEP, in order to monitor the lipid order of the different membrane. That's a lifetime image for conventional confocal microscopy, and that's a lifetime imaging for our image scanning microscopy. So here we make analysis of the data by conventional fitting routine. As you can see here, since it's a confocal image, it's a pretty low signal to noise ratio, and all the purple pixel means that your fitting failed. So you cannot really get the lifetime information because you don't have enough signal. On the other side, by image scanning microscopy, you enhance the signal-to-noise ratio of your images, and thereby, as you can see, basically you can fit all the points of your sample. So the same conclusion can be also obtained if we analyze the lifetime, not by fitting, but using the phasor approach. I'm sure that that during the previous day, you touched quite a lot of this topic. I don't have to explain you about the phasor. So here is the phasor plot for the confocal image. Here the phasor plot for the image scanning imaging. As you can see, the phasor plot for the image scanning image is there is much less noise, simply because, again, the signal-to-noise ratio of the image is much higher. So if, for example, we want to discriminate two different regions of the phasor plot in order to distinguish between order and disorder phases, if you do in the confocal image, you will end up with an image that barely you can distinguish between, for example, the plasma membrane and the vesicle inside your cell. While if you do the same operation on the image scanning microscope image, you can clearly better resolve the plasma membrane and the vesicle that are inside your sample, inside your cell, and which show clearly a different order for the lipids. Okay, so one of the when we implemented this time tagging platform, so basically it's a system that is able to record for each photon a temporal signature with a precision of a few hundred 30 picoseconds. We immediately realized that our computers saturate really fast. So in the sense that if you want to collect this kind of information, you need a big computer, then you need to store this data, you need to analyze this data, and that can be quite difficult to do. So we decided to implement also a second architecture based on the digital frequency domain approach, which is basically, I don't have time to explain you the detail of that, but the basic, the major difference with the time tagging approach is that now you just recording the histogram of the photon arrival time, and you do not recording the information at the single photon level. So this clearly is a disadvantage for many other applications, but in the case of fluorescence lifetime, this is more fluorescence lifetime imaging. These information are more enough to get a map of your lifetime. Okay, so I still have few minutes, so I will go really fast, but I want to give you a highlight of another important project that we are running into the lab that is using the SPAD array in the concept of fluorescence fluctuation spectroscopy. So since we are using a laser scanning system, and you have to raster scanning your beam across the sample, this is not the method of choice for fast imaging. But on the very same architecture, you can implement the fluorescence correlation spectroscopy, and in this case, observing molecular dynamic with a temporal resolution much faster than any other fluorescent technique. So here I want to show you the advantage of having a SPAD array in combination with fluorescent fluctuation spectroscopy. So as I'm sure you know, in a fluorescent correlation spectroscopy experiment, what you do, you record with your single element detector the intensity fluctuation generated by the molecule entering and exit from the probing volume, probing region of your laser scanning microscope. Then you analyze this such intensity trace, typically using correlation, and then you can extract the information like the diffusion of your molecule or the brightness of your molecule. Now that we have our SPAD array detector, basically you collect an image of the probing region, or otherwise you can see that you collect one intensity trace for each element of your SPAD array detector. So in this case, you collect 25 intensity trace. Each intensity trace is associated to a specific element of the detector, so it's associated to a specific position inside the probing region. So given this multidimensional data set, this 25 intensity trace, we can start to analyze using the most conventional correlation technique. So I just want to show you only one example in which we use this new data set to implement spot variation FCS. So spot variation FCS simply consists in measuring the transit time, or more in general, the diffusion of a molecule at different detection volume. And in the case of SPAD array, this detection volume can be easily obtained by summing up the pixel of the detector. So for example, using only the central element, we end up with a probing region of with a size of 141 nanometer. If we take 3 by 3 element, it's 184. If we get 5 by 5 element, it's 280 nanometers. So, but what is very important, that at the same time, we can measure diffusion at different volume. When we get these 3 values of diffusion, or in this case, transit time, but here I report also the diffusion, and we plot as a function of the volume. In this case, we can see that if we fit with a line, the line is passing through exactly to the 0 of my graph, which if I go into the diffusion law, graph, I can see that means that my molecule are diffusing all over a free diffusion. So that's exactly the case, because this was simply some probe diffusing in PBS. But let's see something more exotic. So here we use the spot variation to measure diffusion of different AGF labeled protein in different cell system. So the first line represents GFP free diffusing in the cytoplasm. As you can see, this is confirmed by the diffusion law. Again, if we make a fitting for the 3 points that we obtain simultaneously, the transit time or diffusion time that we obtain simultaneously from our detector, the line passed through the 0 point, which means free diffusion. This other example is more interesting, because here we are monitoring, we are studying the diffusion of DEC. That is a protein that is well known, that is interacting with the DNA. So if we measure the diffusion of DEC outside the nucleus in the cytoplasm, again, we observe a free diffusion. But if we measure the diffusion law inside the nucleus, now we can see that is not anymore, the diffusion is not anymore following a free distribution, but is following microdomain behavior. Because here, the line is not anymore passing to the 0, but is intersected to a positive value, the diffusion axis. So I think that I finished, because I don't want to go too much longer. And what I want to say, what is next? So clearly, what we are doing is to combine fluorescence lifetime with fluorescence fluctuation spectroscopy, because now we have all the architecture available to do that. And let me conclude my talk giving a sort of let's say vision for this kind of project. So as I show you, I hope that I was able to convince you that by replacing the typical single element detector that you have in a confocal microscope with our SPAD array detector, we can improve the spatial resolution. In this case, I show you that we use image scanning microscopy. We can improve the information context, because we can combine with fluorescence lifetime imaging and obtain at the same time an high resolution map. We can improve somehow the temporal resolution, because I show you that we can combine easily with fluorescence fluctuation spectroscopy. But that's only the tip of the iceberg. As I told you, we have many other projects. For example, we combine with stat microscopy, with split stat microscopy that has been described before by Luca Lanzano, with 2-photon excitation microscopy, with single molecule tracking. Before there was a nice, super nice talk about this topic. We also use that for photon correlation analysis, and for adaptive optics. So here is a list of publications which regard from our group concerning this project. So finally, really, the most important thing is that this kind of system is, I think, that for the first time give you somehow the possibility to get access to some single photon information that typically are discarded in a conventional microscope. Not only temporal information, but spatial information. So I think that we are ready to move from what is the area of single molecule to the area of single photon microscopy. With this, I want to thank all the members of my group.